Good afternoon. I am Abhin Krishnan, a PhD student with Professor Sujit in the Department of Aerospace Engineering in IIT Madras. I work in the topic of screeching combustion. Screech usually refers to the high frequency transverse mode combustion instability which is usually observed in ramjets and afterburners. Screech derives its name from the high pitch audible sound that accompanies this phenomena. The objectives of the study include to know what causes screech, how the transition happens from combustion noise to screeching combustion, and to understand the physics behind screech and to come up with a numerical model. The test facility includes a preheater, a plenum chamber and a rectangular test section. The air is preheated to a temperature of 900 Kelvin, thus simulating afterburner inlet temperature, and the vitiated air enters the test section through a plenum chamber. The test section is 1 meter long with a rectangular cross section of 240 mm by 25 mm. The photograph shows the airline assembly leading into the preheater. Then this photograph shows the test section with the plenum chamber. The plenum chamber is 600 mm in length and 600 mm in diameter. The test section consists of 3 pairs of side plates. All of these side plates can be replaced with quads to facilitate optical diagnostic tools. Now the proposed methodology is to map the entire stability regimes of the combustor by varying the equivalence ratio, and then do simultaneous pressure and high speed imaging to understand the transition from combustion noise to screech. Thank you.
Yeah, good evening everyone. I am Manish, PhD scholar working with Dr. Srikrishna Sahu sir and Thermodynamics Laboratory, IIT Madras. My topic is for the poster presentation is experimental study of droplet clustering in polydisperse spray. The main objective behind the study is to find out the cause and consequence of droplet clustering. So what we are doing is that we are using 2 statistical methods. The one is box counting method, the other one is radial distribution function. In box counting method, the spray image is divided into boxes, and we are finding out the probability of the concentration, and we are comparing it with a Poisson's distribution. Then and we are finding out a parameter called D1 parameter. In radial distribution function, what we do is that we find this probability of finding a second droplet at a given separation distance from a reference droplet compared to the case where the droplets are homogeneously distributed. The main concept behind this is that when the RDF is greater or radial distribution is greater than 1, we can tell that there are clusters are present, or when RDF is less than 1, we can say that there are voids are present. Now to find out the diameter of the droplets, what we are doing is that we are using an ILITS technique. ILITS is also known as interferometric laser imaging for droplet sizing. So basically we can get the droplet diameters by using ILITS techniques, where we defocus the camera and it is obtained by the interference between the reflected and first order refracted rays. Now here we can see that the average velocity of droplets has been plotted by using a double pulse Nd:YAG laser and double shutter camera, and the velocity variation was observed from 8 meter per second to 3 meter per second in the radial direction. Now the various mean quantities and fluctuations were also plotted, and we can see that in the spray the cluster length varied from say around 200 to 600 pixels, and this was the maximum value of the RDF clusters. We can also see that the clustering increases with mass loading, and the length scale of the clusters was found to be nearly constant at 150 by 150 pixels. Thank you.
Hello everyone, I am Divya Raja from IIT Madras. The work I am going to present here is the miniaturization of spray nozzle geometry. This work was done in collaboration with the Penn State University. So what I do is I design the processual atomizer in a miniature scale. Say I call it as a 1x atomizer. Then by keeping the design as same, I just scale the atomizer to 3 times, 5 times and 10 times. These atomizers are geometrically scaled. So we performed the experiments by varying the pressure. We measured the flow rate. So flow rate of 1x atomizer, 3x atomizer, 5x and 10x atomizers. By measured the 1x atomizer actual flow rate, and we scaled the flow rate by area times, and the predicted values are like it's linearly scaled, and it was much higher predicted. The predicted value of higher atomizers may be that due to the air core structure is very for a micro atomizer to the macro atomizer, and we do the SMD of the drop size, SMD of SMD measurements for atomizers, different atomizers, by keeping the Z by d over location as 19 for all the atomizers. We found that by operating the same Reynolds number, the axial velocity and the diameter are all scaled as the geometry is scaled. So we calculated the cone angle parameters also. The cone angle of 3x, 5x and 10x atomizers are scaled very well, but when we compare to the 1x atomizer, there is markedly different profile. So by this study, what we can do is, we can find an optimum range of scale factor to yield a good atomization. Thank you.
Good evening. I represent Spray and Droplet Research Group in IIT Madras. Here is a brief overview on the research facilities in our lab. We basically work on the characterization of sprays and droplet using optical techniques. This is the first work, shows the flow around a evaporating droplet. In the left side is the internal flows inside a methanol droplet. We can see that this effect is called Marconi effect, and in the right we have the external flows developed in for an ethanol droplet. This is obtained using a PIE facility, and the next work is on the characterization of atomization of a non-Newtonian droplet. The most of the research investigation pertains to the Newtonian droplets only, so the interest is to see the difference in secondary atomization for an Newtonian droplet, that is water, and a non-Newtonian droplet, that is molten beeswax, is studied here. In the third work, we studied the evaporation in a urea water droplet. The interest behind the study is that the modern diesel engines, to reduce the NOx, we use selective catalytic reduction, which uses urea water. The peculiarity of urea water is that the evaporation is characteristic of urea water is very different from the normal fluid, and that can be seen by the phases of evaporation of urea water. And the last work is on the droplet collisions. This shows the different phases of droplet collision with different relative velocities. And this is a small overview of the work done in our research facility. Thank you.
My name is Raju. My research topic is pre-characterization of novel flow blurring injector. This injector is a new injector which is different from the other atomizer. In atomizer, we have fine and droplet results in faster vaporization, increased free mixing of fuel and air, low flame temperature and cleaner combustion. This is the flow blurring injector which enhances the atomization. This is the typical line diagram of the air blast atomization. While H by D ratio is greater than 0.25, we will not get any atomization, we will not get any droplets. While reducing the H by D ratio 0.25, we will get the stagnation point at the exit of the orifice, so the fuel air is mixing inside the which creates the recirculation bubble in the fuel tube, so it enhances the fuel and air mixing, which enhances the atomization. This is a typical diagram for the air blast atomizer and the flow blurring injector. These are the typical results which is available in this corresponding to reference. From the flow blurring atomizer, we will get the fine atomization when compared to the air blast atomization. The typical droplet size is the 12 to 10 microns. For effect of ALR ratio and atomization, while increasing the ALR ratio also, we will getting the uniform pattern for the flow blurring injector. This is the typical air blast atomizer. We will not get any uniform distribution over the ALR ratio. This is the plot which is. So this is the geometrical parameter. Based on that, we will measure the spray cone angle. We will get the maximum spray cone angle for this one. These are the experimental setup available in our IIT Hyderabad. This is the typical modular design for the 3D printing. These are the experimental setup we are planning to implement.
My study is basically regarding the atomization characteristics of coaxial injector. In that itself, a particular injector called gas-centered swirl coaxial injector, and the motivation behind this study is rocket injectors working under staged combustion cycle, wherein we are introducing a gaseous oxidizer and a swelled fuel. And my study is regarding understanding the effect of a parameter called rhesus in the atomization characteristics of gas-ended swell coaxial injector. So we are actually looking into the spray characteristics of this injector when we are changing this parameter called rhesus. And using the available techniques, we are taking the data using digital photography, MALVAN as well as phase Doppler interferometry. And from the results, we have seen that some interesting phenomena are seen at some particular conditions. We are trying to characterize these things using one spray parameter called momentum flux ratio. And it is seen that there is a variation when we are going from the coplanar configuration to the more rhesus configuration. Thank you.
Biodiesel from avocado has a great potential in India. Its potential has either been identified or underutilized. If you can see the chart from here, avocado is one of the largest producing oil next to coconut and palm. The properties of avocado biodiesel are also to be found to be much in comparison with diesel, and the performance has also been seems to be in comparison to diesel. You can see an increase in the specific consumption by around 3.5%, yet there is an increase in brake thermal efficiency by 6%, decrease in CO emissions by 12%, and decrease in HC emission by 7%, except for increase in NOx, which has to be studied. And all those results have been published over here. The main advantage of growing avocado is we are not conflicting between food and energy. We have around 2 lakh hectares of tea plantations in Tamil Nadu where we can plant avocado as an intercrop, and yet we can produce the fruit, and it does not have much competition between food and energy. Thank you.
The topic of my poster is the composition based investigation of biodiesel fuel. What we are trying to achieve here is to develop a phenomenological model for the prediction of physico-chemical properties and combustion parameters. Apart from that, we are trying to model emission as well based on the composition of biodiesel fuel. As of composition, what we know is composition of biodiesel fuel is further classified into saturated and unsaturated methyl esters, which directly affects the physico-chemical properties of the biodiesel fuel. Now, because of this alteration in the composition, we will have its effect on the different parameters in the engine experiments as well. Now, what we have done here is we have generated our own data with the engine experiments what we have done, and we have compared the data from the formulations. Apart from that, we have measured the different physico-chemical properties as well, and we have prepared a formulation. We have derived a formulation which is comprised of 2 different parameters: the modified degree of unsaturation and straight change saturation factor. These 2 parameters are incorporated in the formulations, and when we got the results from that formulation, we compared it with the measured data, and as you can see from the results are matching well. The errors are well within the plus minus 2% of error. And from this you can see the trends as well, like with increase in temperature there is a decrease in kinematic viscosity, density as well as surface tension. So till now these 3 physico-chemical properties we have developed a formulation, and we will further try to formulate for different properties as well. Thank you.
This is my MTech project based on microalgae cultivation in bubble column photobioreactor and production of biodiesel. Biodiesel is an environmentally friendly fuel which is CO2 neutral, and it is having lesser amount of pollutant content. And microalgae can be cultivated because microalgae is having higher amount of lipid content and high CO2 sequestration capacity, and it can be used for the production of biodiesel. And microalgae can be cultivated efficiently with higher growth rate in a bubble column photobioreactor. This is the design of the bubble column photobioreactor, which is having higher H/D ratio of 5, and it is an illuminated cylindrical vessel which consists of sparger, a plate which is attached to a gas chamber, and air is passed through the holes provided in the sparger, and it helps the mixing of the algae culture. And these are the properties of the algae culture which is taken at the 8th day of the cultivation. And this is the open pond cultivation as well as conical flask cultivation done parallel to the cultivation in bubble column photobioreactor. And these are the theoretical prediction that is done in MATLAB and these are the volumetric mass transfer coefficient, and these are the gas hold up value which is increases as gas velocity present in the gas chamber is also increases, and the production of the biodiesel will be done in future.
The major part of my work was to do a numerical study of parallel panel test using a software, CFD software called OpenFOAM. The major idea behind this work was to take a ISO standard case where you assess the flammability of the materials, where you have a propane burner and two vertical parallel panels sitting above the burner. And I simulated the parallel panel test and then I did a parametric study in terms of geometrical values like the thickness of the panels, single versus double panel, etc., and under different gravity environments. The second part of the study was doing a sensitivity analysis of the whole test with respect to the solid fuel parameters. Again, heat release rate was taken as the major output, and I tried to perturb the quantities from the base values of corrugated cardboard material. And I did a sensitivity analysis where I plotted the sensitivity of various fuel parameters like activation energy or thermal conductivity or emissivity. And this study will then will be useful for later getting FPA data where you have to be accurate in the parameters you get.
Myself Rajan Lanjekar, working under Dr. Deshmukh sir from IIT Indore. This is my topic, modeling pure fatty acid ester spray. We are modeling the fatty acid ester spray because fatty acid ester spray is the pure component which plays the composition in the biodiesel. Biodiesel composed of pure fatty acid esters. By observing the liquid length difference by varying the chain length from butyrate to palmitate, we are saying that if we vary from 5 to 16, there is a chain length variation as well as the liquid length variation. So higher the chain length, higher the liquid length will be there. And by varying the methyl palmitate to ethyl palmitate, by varying the alcohol moiety from methyl palmitate to ethyl palmitate has the higher liquid length as compared to the methyl palmitate. So in this simulation, we have done this simulation with the help of the OpenFOAM code. We have implemented the fuel methyl palmitate, ethyl palmitate with the help of DI-PBr database, and the conclusion of this work is the compositional effect is validated. Compositional effect is seen on the liquid length. Mainly the chain length effect is the more prominent one compared to the alcohol moiety. So these are the references. This is conclusion. Okay, thank you.
Good evening, I am Rakesh from IIT Hyderabad. So this work is all about the spray characterization for isooctane at elevated pressure and temperature conditions. Nowadays gasoline direct injection is a new trend for SI engine. The speciality of this concept is that the fuel stratification is very helpful for the enhancement in the engine efficiency. There are two concepts. One is homogeneous charge formation, and second is the stratification. During stratification, fuel is injected at a higher pressure and temperature conditions. So what we are doing is, we are trying to mimic the engine like higher pressure and temperature conditions. So for this reason, we have developed this constant volume combustion chamber. Idea is, we send a predefined amount of air and acetylene and pressurize the chamber. And we do the combustion of the air and acetylene. Because of this combustion, the pressure and the temperature inside the chamber increases. After that, this combustion product will leave their heat to the surrounding, and the pressure and temperature will go down. So when the internal condition reach to a specific pressure, the fuel is injected inside the chamber.
and these images we are capturing then with high speed camera. For the vapor penetration length we are using the slurring technique, and for the liquid we are using the Mies scattering. So we can see that these are the vapor penetration and this is liquid penetration. Vapor penetration goes on increasing with time, but the liquid penetration gets settled down after some time because of the evaporation. As the internal temperature and pressure increases, the liquid is settled down, and that's all.
I am Malinayam Raman from Clean Combustion Research Center, King Abdullah University of Science and Technology. Our research team is proposing a new kind of fuel that has a higher energy density for aircraft and engine application. In this research work, we are just proposing a fundamental research study on ignition for the two unique molecules that has higher energy density. Coming into the production side, this pinene, which is a new molecule that is produced from pine tree, is produced by steam distillation process. The resins collected from the pine tree are kept in a reactor and steam is fed into the reactor. The lower boiling fractions present in the reactor escapes the reactor and it is condensed in a condenser to collect pinene that has a unique molecular structure. If you see, it is a strained molecule, and if you add orthophosphoric acid with this pinene at respective stages, you can collect pine oil, which is a combination of pinene and terpenol. Here terpenol is a tertiary alcohol with oxygen in its structure. In order to meet out the demands in the future, researchers from Georgia Tech are trying to produce this pinene from bacteria, from sugar, using inexpensive bacteria as a catalyst. In this way we can meet out the demands. Their target application is aircraft, and they are trying to use this as a jet fuel. So if you compare the properties of this pinene and terpenol with commercial fuels, you see that the calorific value, that is the energy density of pinene, is very higher, which is higher than even petrol and diesel. So when you compare with other biofuels like ethanol and biodiesel, it has a very higher energy density, and this is the important advantage of this fuel. We characterize the ignition attributes of this fuel in an ignition quality tester, and we have measured out the ignition delay. If you see that terpenol and pinene has a longer ignition delay, closer to isooctane, and therefore we can use it as a fuel in SI engine applications. When you compare this pinene and terpenol with ethanol, there are two advantages. One is the higher energy density and another is the lower latent heat of vaporization. From the results you see that terpenol has a longer ignition delay, 104, and from the ignition delay we computed the RON value, which is 104, closer to isooctane. So in future both pinene and terpenol can serve as a potential fuel for SI engine applications. This project comes under Future Fuel project headed by Professor Mani Sarathi, and in KAUST we are also involving in some other projects in diesel engine, SI engine, CFR engine, headed by Professor Dibble, and Professor William Roberts is taking care of high pressure projects with Clean Combustion Research Center. Thank you.
Hi, I'm Ruchika Agnihotri from Indian Institute of Science. My topic is new high temperature tolerant catalyst for hydroxyl ammonium nitrate monopropellant. Monopropellants are basically single component propellants which can be decomposed using a catalyst for thrust applications in space propulsion. They are used in micro and nano satellites. Application is mostly in control thrusters. The conventional monopropellant include hydrazine and hydrogen peroxide, but hydrazine has got certain problems such as high vapor pressure, high toxicity, and high storage and handling cost. So it can be substituted using hydroxyl ammonium nitrate since it's a ionic liquid. For hydrazine decomposition, we have got Shell 405, that is on-shelf catalyst. For HAN, usually proposed catalysts are precious metals over various supports. We have tested two sort of catalysts. One is a duplicate of Shell 405, that is iridium supported over gamma alumina, which is prepared using wet impregnation process, and then unsupported catalyst, which includes cerium oxide doped with transition metals. So it goes through from process. First process is catalyst synthesis, powder synthesis, then we go for forming operation, and later on sintering to form final pallet. This is the regular schematic of batch reactor what we are using. Done? Okay. catalyst evolution we have performed using thermal analysis and batch reactor analysis. We have shown that 2% dope cobalt in cerium oxide has shown performance close enough to iridium doped over gamma alumina. It can be seen in DSC curve as well as TGA curve. It has shown similar performance in case of batch reactor as well when it is done at isothermal temperature conditions. The pressure raise is equal to iridium doped over gamma alumina, and it can sustain up to 50 cold starts, whereas iridium doped over gamma alumina can sustain only 15 injections.
Hi, I'm Milind from Forbes Marshall. This topic is around the fuel feasibility evaluation and fuel flexible combustion system design for the process industry application. It's basically a customer in India has a plant to process the marigold flower, and as a part of that they are getting a byproduct in the form of this lean wax and lean layer. So they approached us whether we can design a system which can burn this fuel and thereby reduce the cost of discharging that effluent, and also replacement cost of the existing furnace oil. So as a result, we analyzed and we found that from the basic proximate and ultimate analysis, the properties of the fuel when it is melted are much better than the existing fuel, but in the solid state they are very different, and like it is much harder than the tar. So the challenges involved there were like the solids phase when it was in the ambient, and also the higher viscosity. Also in some variants there was the water content was very high, and from batch to batch the product quality was changing significantly in the range of 5 to 10%. So we had to design a system which could cater to all these issues, and also make the system operable consistently throughout the time without having some effects of combustion, emission, corrosion, other thing. At the end of the system, we could develop a system for the customer, and now it is operational for almost more than 6 months, wherein we have replaced, and customer is saving on both the fronts. So that's the outcome of this research. Thank you.
Myself, Sivaram Krishna from Indian Oil R&D Center. Today I am here to give presentation on novel energy efficient process for multi-feed gasification. Coming to the background, today there are no gasifiers commercially available which can handle all type of feedstocks. In Indian Oil R&D we have developed technology which can handle all type of feedstocks. This technology is two-stage gasification, where in first stage gasification coal and biomass are introduced, and in first stage gasification ash and other contaminants were removed, and the gases that are generated will be sending to the second stage gasification, where in second stage gasification we will introduce pet coke feedstocks like pet coke, shale oil, lignin and asphalt type of feedstocks, and finally we will be generating very pure synthesis gas.
Hello, my name is Jagannathan. I am a PhD research scholar in IIT Madras, and my work is going to be about biomass gasification conversion of derived fuels. So what we are trying to do in this project is we are just trying to gasify biomass in a counter current gasifier. Okay, we are counter current gasifier means we are supplying the air from the bottom and we are igniting the biomass from the top, and the air, flame and the air is going to be coming in opposite direction. So that's why it is called as counter current gasification. And what we are trying to do is we are using 16 types of biomasses over here of variety of composition and variety of sizes and shapes, and we are just plotting the graph against the superficial velocity, different superficial velocity to the mass flux of the reactor. And we are able to find some interesting fact over here is after a particular superficial velocity of the gasifier, we can able to find a universal trend. That is universal. The mass flux is going to be almost constant with respect to the various superficial velocities. This is going to be an interesting phenomenon which says that even though you increase the superficial velocity behind this particular range, the fuel flux is remaining constant. That means the efficiency is being fixed and your maximum conversion is being fixed for variety of biomasses. So that is the main output of this work, and the same has been modeled out, and the model, this model has very less effect, says that the combustion of the biomass in this particular counter current mode has very less kinetic effects, and this is a physically diffusion controlled model, and the model behavior is going to be very well suited with respect to the experimental results, and the model results are shown over here. And so now currently we are working here is, we are just trying to trying to modify the gasifying medium into carbon dioxide plus O2 mixtures, and we are trying to gasify the CO2 to CO, so that we can able to have some carbon sequestration potential, which is a useful benefit to the society. That's all. Thank you.
As we all know, microalgae are very rich in lipid content. That's why we have been using microalgae for this biooil production in this experiment. We are using fast pyrolysis. We are using fast pyrolysis of microalgae to give value-added chemicals as well as biofuels. As we know, nanochlorosis proves to be a very good source of lipids, and hence this quantity and hence this property of lipids is used for the production of biooil. And as we all know that the catalyst, we have done the characterization of the catalyst and the feed. The catalyst characterization has been done using the ICP OES. We have tested the thermal stability of the catalyst. We have done the BET porosimetry of the catalyst. We have done the ammonia TPD of the catalyst. As we have the very high lipid content of nanochloropsis. The volatile matter 63.36% is also considered to be the very high thing. Then the our experimental setup, it consists of a micropyrolyzer coupled with a GC and MS. It's a Shimadzu QP2010 equipment. The micropyrolyzer is coupled. It's like the pyrolysis experiments occurs in micropyrolyzer, and the vapors travel through helium in the GC and then quantitatively, then qualitatively analyzed in the MS. And then we have the MS separates the compounds on the basis of MZ ratios. These MZ ratios are being characterized and then converted into various groups of chemical compounds, and this all we can see. We have to first optimize the temperature. Upon optimization of temperature, we got the maximum hydrogen, hydrocarbons and benzene derivatives at 500 degrees centigrade. Then we have induced the catalyst. Our catalyst is already proven to be a very good catalyst in hydrodesulfurization industry. So that's hydrodesulfurization is essentially very much same as hydrodeoxygenation. So that's why on the notion that our catalyst can perform deoxygenation also, we have chosen this catalyst. When using this catalyst, we got a very special chemical with a mixture of aziridine to carbonitrile and dimethyl ketene. Dimethyl ketene is a precursor for polymers, and aziridine to carbonitrile is used for anti-cancer drugs. We have done various metal loading, the effect of metal loading on the product composition. We have done the effect of temperature on the catalyst. We have also done the char analysis, which will come in subsequent results.
So this work essentially looks at how the chemical pathways change in a turbulent premixed hydrogen-air flame. So how the pathway is well understood when we look at laminar unstretched hydrogen flames. The intention of this study is to see how turbulence essentially changes this particular picture. Turbulence can manifest itself in multiple ways, one of them being how curvature and straining are affecting the flame surface, which could essentially lead to local pockets of fuel and eventually lead to change in kinetics. Increasing turbulence also decreases the diffusion time scales, and as a result of which they can become comparable to your chemical time scales. This in turn can also lead to diffusion of species from one location to another, again altering kinetics. And finally, there's always the effect of the small scale eddies altering the flame structure. This work is primarily done through numerical simulations using DNS of lean 0.4 equivalence ratio hydrogen-air flames. The work essentially starts with taking an isosurface in order to define the curvature and the straining, and defining normals based on the temperature gradients in order to extract the reaction rates. The reaction rates, once extracted, can be integrated in order to give a line integral, and these can then be added up to eventually give a point effect, which are plotted in the results.
We've also done stretch flame calculations using Obdiv, which have counterflow frames, and once you have this 1D information, this can also be integrated to give you a point effect. So we now compare results from the numerical simulations and the stretch frame calculations. The ones with the solid lines show the stretch flame, and the ones with the dotted ones show increasing turbulence intensities. It is interesting to note that you really do not see much of a change between the turbulence and the stretch flame calculations, and laminar stretch flame calculations can very well predict what the kinetics or the chemistry is going on in the case of turbulent hydrogen air flames. We've also conditioned them on progress variable, which is essentially defined based on your fuel consumption and is shown here. And a small C-bar corresponds to a location which is much closer to your leading edge. These leading edge do show trends which are a little different than the global flame characteristics. However, the trends still remain the same. So the effective conclusion from this work is that whether we're looking at turbulence ranges or whether we're looking at stretch flame calculations, you can very well predict them even within the bands of stretch flame calculations without showing much of a change in chemical kinetics. We intend to look at other conditionings in the future as well. Thank you.
So myself Deepak Ojha, so we work on fast pyrolysis of bagasse and groundnut briquettes. So the briquettes are one of the raw material for the boiler and smaller scale industries. It is used for combusting and heat generating and steam generating. So, and fast pyrolysis is a promising technology to produce bio-oil, and this bio-oil that can be used later on as a transportation fuel later on. And as we all know that the majority of the products spectra of the fast pyrolysis is liquid bio-oil. So around 60 to 70% of the yield will be bio-oil, and 15 to 25% is going to be solid char, and the rest is condensable gases and non-condensable gases. So we are going to study. So let's look at the carbon cycle of the process. So these are the agro crops that can be made to agro residue, and this agro residue can be briquetted, and after briquetting it can either be combusted or it can be pyrolyzed, and bio-oil is produced. So this bio-oil will be later combusted in normal boiler engines, and char also one of the residue that I said that can be combusted, and the net CO2, whatever we can say that is generated out of combustion of the briquettes and the bio-oil, that can be recycled in as a photosynthesis in the crops. So that's why it is called the carbon neutral process. So here we are going to estimate the kinetic parameters of the degradation of the biomass briquettes. Then we are going to study the typical product spectrum of the pyrolysis. We are going to understand the product and reaction time scales of the pyrolysis, and so here we are going to use the By-Job-Keane method for the activation energy calculations, and we are going to carry out the experiments in pyrolysis, and we are going to analyze the product by using the GCMS. The time scale study were carried out using the pyrolysis FTIR setup, that is online connected. So these are the feed characterization. Feed characterization says that there is not much variations in the approximate analysis values, but there is a variation in the elemental compositions of the biomass based on the particle size. So this is the degradation profile of the bagasse and groundnut. We can see that the majority of the degradation is taking place below 400 degrees centigrade. It's almost going to be similar for these two cases. This is a TGA and DTG profile. So the activation energy is going to be in the range of 100 to 280 kilojoule per mole for these two components. Products, the majority of the products is going to be the phenolics, and you can see that small variations in the product quantity based on the particle size. There is not significant variations in any of the components. Time scales, if you look at, we can see that the pyrolysis is going to complete within 12 seconds. The maximum product evolution is reported at 12 seconds. After that it is decreasing finally, and the reaction is starting at 6 seconds onwards. We are started getting the products. Then look at the effect of particle size and temperature on the pyrolysis time scale. We can see that there is significant reduction in the pyrolysis time scale. The pyrolysis time at 500 degrees centigrade is around 50 seconds. That is reducing to 7.5 seconds for 800 degrees centigrade. And if you look at the particle size, we can see that there is not much significant, there is no significant variation in the time scale with the particle size. But still, if you move to 0.25 to 1.40, there is slightly variation of 1 to 2 seconds in the pyrolysis time scale of the reactions.
Hello, my name is Abdul Ghani. I'm a PhD student associated with the Clean Combustion Research Center at King Abdullah University of Science and Technology. My work mostly deals with the combustion of heavy fuel oils. Heavy fuel oil is residue that is obtained during the distillation of crude oil, and it's a residue which is highly viscous, and it is used on marine engines and also in boilers for electricity generation. It has a lot of sulfur content, and it has caused a lot of environmental problems, and our aim is to design a mechanism and to design the fuel such that the combustion happens in such a way that the fuel is cleaner. So right now we are trying to characterize the fuel. We are exploring the different options in which the structure of the fuel can be characterized, and one such option is nuclear magnetic resonance spectroscopy. We did before we do that we did a mass spectrum. We identified like around 12,000 different components in heavy fuel oil, and it's not possible to identify the structure of all these molecules, and it's also not useful. So we are using NMR spectroscopy. NMR spectroscopy is the technique in which you can identify the structure of different types of hydrogens and different types of carbons. And using this, we are trying to characterize the fuel in 3 different techniques called average molecular parameters. In this technique, we are finding the different types of hydrogens like aromatic, polyaromatic, olefinics, paraffinic hydrogens, and also different types of carbons. And this gives us one way of characterizing the fuel. And using this data, we have defined 19 functional groups, and we are calculating the concentration of these functional groups using NMR. And at the end, we have also developed a surrogate molecule. This is an average molecule that represents the entire structure of the fuel. It has the same carbon to hydrogen ratio, it has the same paraffinics and the aromatics and the naphthalene content that we see in heavy fuel oil. This molecule can be used as a surrogate for developing detailed combustion mechanisms. I would like to thank the organizers for giving me this opportunity. Thank you.
The work is on oxidation and combustion kinetics of biodiesel. So right now we are working on auto-oxidation. It's basically a liquid phase phenomena. So there is a need for understanding the auto-oxidation and combustion kinetics of biodiesel. And the objective is to formulate a reaction mechanism for liquid phase oxidation. So we have obtained the skeletal auto-oxidation kinetics scheme from the literature, and the experimental data of aged biodiesels are obtained from the literature, and a genetic an optimization using genetic algorithm is used for obtaining the optimized kinetic rate parameters. So this is a Ransimat auto-oxidation stability measuring device, which is known as Ransimat apparatus. It basically contains a block. This it has a 3 gram of biodiesel fuel, and air is supplied through it. As the auto-oxidation proceeds, the temperature is kept at 110 degrees Celsius. The air carries the volatile acids to this conductivity cell, which contains water, distilled water, and as the volatile fuel dissociates, the conductivity suddenly shoots up. So the sudden shooting up of conductivity gives a induction period. As the induction period increases, the auto-oxidation stability increases. So these are the results which are obtained for rapeseed methyl ester fuel and soya seed methyl ester fuel at 110 degrees Celsius. The dotted lines are basically the experimental data which are obtained from MNA, and straight line gives the numerical simulation using chemical kinetic modeling, and so we can obtain that it's more or less good trend and prediction is obtained using the chemical kinetic modeling of the auto-oxidation phenomena. And the further step in this process is identification of reaction scheme for ignition and combustion kinetics of biodiesel, and these are the references, which is Zebernik, that is using chemical kinetic modeling of jet fuel auto-oxidation, then the experimental data obtained from MNA, and thank you.
Our aim is to develop a simplified kinetic mechanism for syngas combustion. From the previous data of Varun sir's experiments, we came to know that the CO emissions coming from a biomass gasifier are very much different from the equilibrium assumptions, and hence we can say they are kinetically controlled. So, and what the mechanisms are which are available right now are not able to predict CO emissions and temperature correctly. The reason is these mechanisms are optimized for laminar flame speed and ignition delay, and the CFD results also show the same thing from Mark and Zuritsky paper. Initial set of experiments what we did is this is a diffusion flame. This is a diffusion flame. The biomass combustor what we are developing is a diffusion flame combustor, and we use CFFR and SBF2 mechanisms to predict the CO mass fraction and temperature. And this CO mass fraction and temperature we try to match from the experimental data. What we came to know that these two mechanisms are not able to predict the temperature and CO mass fractions correctly. So there is a deficiency of mechanism. Now what we do, we use a very small and open jet flame, and right now our future work is to verify these mechanisms to show that these mechanisms will not work for the diffusion flames, and to predict a new mechanism with the experimental data and try to match with this experimental data and try to give it to a practical combustor device. Try to give it to a practical combustor device, and in that also it able to predict CO emissions and temperature correctly. Thank you.
So the future equipments and future demands depend upon the legislation. The legislation is to meet the drivability as well as fuel consumption and emission. So in order to achieve this, we need to understand the quality of the combustion. So the combustion is always in automobile industry we use a normal cylinder pressure sensor. With the help of the cylinder pressure sensor we cannot able to distinguish the difference between the premixed flame and the diffusion flame. So in order to understand the quality of the combustion we need to understand these two things. So for that we have developed, AVL has developed some techniques and these tools. So one is optical research engine and as well as optical tools. With the help of optical engines we can identify and we can visualize everything what is happening inside the engine, and with the help of optical tools we can improve the engine's power efficiency as well as fuel efficiency, torque and everything. So AVL has done some experiment in some engines. In that we have I have shown some example that. So in the GDI engines there is most important thing we are seeing is for valve wetting. So valve wetting is one thing which is most important for emission. So if you see that my objective in this picture is, with the help of endoscopic we have seen inside the combustion chamber there are two intake valves. So in the intake valves the fuel has to be sprayed equally on both the valves. So still if it is spraying, but there was a lot of valve wetting. So a lot of valve wetting means a lot of fuel droplets will occur on the valve. When the next cycle, when the fuel again comes inside, it will be a more droplets, and this will leads to be the more emission. Okay, and according to the when go for this is a conclusion. In the conclusion, we are seeing that with the normal cylinder pressure sensor, we are calculating with the heat release, and it cannot be seen. With the help of this sensor, we can see some flame radiation as well as knock. Thank you.
Yes, good evening. I am Anand from Center for Gasification and Propulsion Laboratory in IISc Bangalore. So this work is mainly focused on developing a catalyst for Fischer-Tropsch process. So the base input for a Fischer-Tropsch reactor would be syngas, which is a combination of carbon monoxide and hydrogen. So the entire focus is to catalyze the reactions which happen in a Fischer-Tropsch process. So my colleague Snehesh has actually developed a catalyst which is based on cobalt. But the novelty in this system is that he has used a combustion synthesized catalyst which compares very well with respect to the existing process, which is nothing but a IWI catalyst method. And well, all these graphs here are trying to prove why this combustion synthesized catalyst is much better. But to just give you a very brief understanding as why it is better, the first thing is the weight fraction versus the carbon number, which is synthesized with this new catalyst, has a much flatter curve instead of a selectivity to a few molecules. And then this shows why the new catalyst has a higher weight conversion with respect to carbon monoxide. And then these are some very basic but very important characterization curves, which shows that the amount of cobalt which is available for catalyzing these reactions are much faster. Thank you very much.
My name is Arvind Gupta and I am from Center for Sustainable Technologies, CGPL Lab, IISc Bangalore. And today I am here presenting one of the works that are being done at the CGPL Lab. And my work relates to the gasification part, that is the generation. And to give you the simple idea of our work is, we want to increase the hydrogen component in the syngas. And if you see the chemistry of the biomass that we have considered is the wood, it is 66H10O5. That means if you see the chemistry, the available hydrogen in the biomass is around 60 grams per kg of biomass. 60 grams of hydrogen per kg of biomass. But if you follow the air gasification that is already existing and it is quite popular, you will get around 41.7 grams of hydrogen per kg of biomass. So in this work, what we have done is, instead of air gasification, we have followed the oxy-steam gasification. In oxy-steam gasification, what we do is, instead of air that is composed of oxygen and nitrogen, we are sending the pure oxygen along with the superheated steam. So what it does is, it increases the hydrogen component in the syngas, the resulting gas more than double. We found out that in our final results, if I want to summarize, I will say that I got hydrogen in the final syngas through the oxy-steam gasification. It was around 104 grams of hydrogen per kg of biomass. That means we were able to achieve more than the double, that is we can achieve from the air gasification. So the additional hydrogen that is coming from is from the steam. So these are the various modeling. We modeled one particle of 10 mm dia of the biomass, and we have analyzed the we have done the analysis and compared with the experimental setup here. This is the experimental setup, this is the model, and these are various weight loss with the time when the pyrolysis takes place, and these are the various analysis, and this is the table when that is between the steam to biomass ratio and the different outputs from the model and the experiments. Thank you.
Hello, I am Rakesh, a research scholar at the Center for Sustainable Technologies, Indian Institute of Science, Bangalore. In this poster, we are discussing the research activities on fuel cells which has been initiated at our department. A fuel cell is an electrochemical engine which converts chemical energy of fuel directly into electrical energy. There are different kinds of fuel cell. Solid oxide fuel cell, which is used for power generation systems, and PEM fuel cell, polymer electrolyte membrane fuel cell, which is considered for transport applications. Research activities on both these kinds of fuel cells has been initiated in our department. Here I am presenting some of the initial results and the future studies in this direction. A fuel cell has very high conversion efficiencies, which helps us in attaining overall efficiencies which are much higher than the conventional systems. So this is explained in this graph. We can see that fuel cells have higher efficiencies compared to the conventional systems. So there are different transport mechanisms taking place in fuel cells, which is explained here, and the different subsystems for fuel cells is also explained here. We have done some initial modeling of fuel cells, which is being explained here. And if we go for power generation systems based on fuel cells, we can see that conventionally natural gas or hydrogen is used as a fuel. Here we are trying to produce a gas which is obtained from biomass gasification as a fuel in solid oxide fuel cells. There are several challenges which is reported in the literature, and tar is a major challenge. We have characterized the tar, and we have seen that the tar level is comparatively very less. So these are some of the major challenges, and we are trying to address some of these challenges and obtain a coupling of fuel cell and gasifier systems.
Good evening. I am Mohammad Shariq Ahmad. I am presenting a poster on development of lean gas burner. I am from Steel Authority of India Limited, SAIL. And blast furnace gas is produced in the integrated steel plant as a byproduct. It is around 1600 Nm cube per ton of hot metal. And the problem in burning the blast furnace gas is that it is having very low calorific value, and so the burning the blast furnace gas requires rapid mixing of gas with the combustion air. In our plant, in boiler number 1 to 5 of the Bhilai steel plant, there were the boiler were of old Russian design, having coke oven, gas, pulverized coal and blast furnace and liquid fuel firing systems. And in blast furnace gas burners, the problem was coming because it was of old design and having premix design, having refractory checkered work and refractory embouchure, so the flame used to come back and hit the refractory checkered work, and it used to get damaged and bricks used to fall. So we proposed a new design, and we took a project to improve this burner design and increase the blast furnace utilization to 16,000 more, enhance the blast furnace gas firing in each boiler to increase by 6,000 Nm³ per hour. So in the new design we have proposed a metallic burner diffusion flame in which in this rectangular slots the blast furnace comes, and around this in the annular space the combustion air comes, and it gets fit in this inside wall of the boiler. Now in this new design, the velocity is also we kept the velocity low, and it is around 10 to 12 meter per second for blast furnace, and tip anchored flame is generated, and it is smooth and bushy, and we have reduced the coal consumption by 21,000 tons per year, and also the greenhouse gas emission and fly ash. So overall, in conclusion, we have designed a better burner with properly anchored flame and with minimum maintenance. Thank you.
This poster is based on the work done for predicting furnace heat transfer along the height of tangential fired boilers, and basically what I have done is I have divided the furnace into different heights, different zones based on the height, and then at each zone I will be calculating the devolatilization characteristics, then the char combustion and the radiation model. The radiation model I have taken the gas to gas radiation, gas to surface and surface to gas radiation, and the typical input for this steady state one dimensional model is the coal parameters, the air and coal flow rate, temperature, etc. And then the physical and thermal properties of coal, ash, like gas, emissivity, porosity, density, and then the furnace geometry. The output of this model is the furnace temperature along the height and the heat flux distribution along the height of the boiler. And one more important parameter is the furnace outlet temperature, which is used for predicting, the designing of the second pass of the boiler. That is a very important parameter. Also we can get the flue gas temperature and the flue gas composition at the exit.
Yeah, the poster is about the identify the potential gap in the heat rate for a 500 megawatt unit, that is at Trombay, India, because of change in the coal parameters. So the unit is by BHEL, and the approach is to find out the potential gap in the heat rate and suggest some correction so as to achieve the desired heat rate. This is about the power plant cycle operation, which is operating on a Rankine cycle. So the design heat rate, which is about 2000, that has been deteriorated to 2100, and due to change in the coal parameter also the efficiency has been reduced from 86% to 83%. So if you see, there is a degradation in heat rate of 258, and due to boiler, the decrease in boiler efficiency, that has contributed 141 kilocalorie out of that. Due to loss in boiler efficiency, there is a tendency that has been affected to contribute to the final heat rate of the unit. So that has been analyzed, and we have seen that because of the decrease in efficiency is mainly because of the high moisture in the coal, higher exit furnace temperature, and the radiation losses. So the slagging and fouling potential has been calculated for this furnace, and it has been seen that the Indonesian coal is having higher slagging and fouling potential, and this is some numerical calculation from where we have derived the slagging and fouling potential. If you see this photograph, that is also seen in the furnace tube, which has been removed during shutdown. Due to the effect of slagging and fouling, there is an increase in the reheater spray and etc. So the suggested measure is about putting some high pressure jet inside the furnace and additional soot blow.